Okay, go ahead.
Okay, so before class begins, I just wanted to talk about the reviewing project. So obviously the reviews are due today at 5. So hopefully all of you have either got them in or you're in a position to add them in. So the last part of the project, so I know you guys have these other homeworks and projects due after Thanksgiving. So the last part of the reviewing project is going to be, so I've set it up so that there's at least 2 reviews per paper. So each one of you has to do 2 reviews, but each paper also has at least 2 reviews right now, okay? So you might have seen this, when you submit your review, somebody already has a review up there. So the last part of the project is going to be a discussion phase, okay? So essentially what you're going to do is you're going to take a look at the other person's review, right? And for example, you're going to talk about some things that maybe they didn't address, right? And the other person's going to do the same thing for you, okay? It's fairly straightforward to do this in Easy Chair. So if you've gone to the page that shows your reviews, right, once it's posted, there's a box at the bottom that says add comment, okay? So the text box, and you can add comments, okay? And it's not restricted. You can add as many comments as you want. So basically what we want is sort of a conversation on the paper, because, you know, 2 of you have spent a lot of time going through the paper and kind of reviewing its weaknesses and strengths and stuff. So we just want to see if there's a discussion going on and if you can come to a consensus in terms of what you agree are the strong points, weak points of the thing, okay? So that stage, basically you'll have a week to do that. So I'll make it due like next Wednesday, just before Thanksgiving, so that that project will be done by next Wednesday, okay? So you guys are done with your reviews now. I'll close the reviewing, okay? And then you can have a discussion phase for a week, all right? So any questions? I'll send an email about this with the details, and you can always ask me questions on email. But right now, does anybody have any questions about that? About the project? No? Okay. Okay, so I'll do that. I'll send an email, and obviously, if you guys have questions, you can. I'm Karthik, by the way. So, I should have started with that, but so you guys can send me email. You can come meet me if you have any questions. But basically, get your reviews in today, and then we'll have a discussion phase for 1 week till next Wednesday. All right? Okay. Thanks. Thanks, Sean. Yeah. Can you edit our reviews again? Look, you can edit your reviews up until the deadline today, until 5 p.m. But then the rest of it is just going to be discussion. Okay. I mean, it's not like we are going to grade you only on the reviews. I mean, the discussion is also part of it. So it's not like the review is set in stone. That's part of the discussion also, to actually, you know, have someone else look at your reviews, comment about it, and then you can maybe defend, you know, your thoughts. And then the same thing for the other person as well. Okay.
So to put this in perspective, actually the best conferences, the ones that you should be sending your papers to, those of you who are writing papers, are the ones that actually take the discussion phase seriously. Okay. The way most conferences work is there are 3 independent reviews at least. I mean, in this particular case, we wound up having 2 independent reviews. The bad conferences, they just add up the numbers, you know, and then take the average and just, you know, take the top K. Okay. The most interesting review, the good conferences, essentially, after your review is done, that's when the fun starts. There is actually a lot of discussion. And it turns out that, first of all, a lot of things can come out there, you know, because you have to understand that, you know, the entire research, as you know, it's basically peer review. Peer review means they are no better than you are. It's not that a teacher is reviewing your paper, okay? So it's not obvious that they understood, that one single reviewer would have understood everything in your paper. Okay, so what happens is there's a lot of discussion about whether they actually did the right problem, whether they completely solved it, whether their approach is good, should we allow it to be presented to the overall community, all this stuff. Okay, and we might show you at some point of time. And most recently I did the ICAPS conference, but I've done AAI before. I mean, ran the AAI conference too, and sometimes the sum total of the reviews in the field that we are in, AI and planning, is longer than the paper. Okay, the reviews and the comments are longer than the paper. And most of the time, the authors only get just the reviews. But there's a lot that goes on behind in terms of the discussion. And you know, in a scholarly sense, the reason you agree to review is sort of for the other people in the field to not only do you get to see the papers, but you also get to talk to other people who are reviewing the papers. Okay, and I make up my mind about who else to call next time around on the program committee based on the care at which they review, as well as the care at which they defend their reviews, as well as the care at which they look at other people's reviews. Okay, so that is the most important thing that you can learn about in terms of, and then, you know, avoid I mean, there are conferences, many conferences where very little discussion takes place after the reviewing, and avoid sending papers there because it's waste of your time, essentially. Okay. So yeah, this discussion phase is actually quite important in my view. That's where you get to take. I mean, ultimately you have to take each other seriously because everybody is equal. At the frontier of research, everybody is equal. There is no teacher and student sort of a thing. And you just have to take yourself seriously. In fact, one of the interesting things that people actually come up with, and I think you did this right now, right? So you don't know the other reviewers' name. Right
yeah,
now.
It's all anonymous.
So there is all sorts of interesting questions. So some conferences make the reviewer names public to each other's reviewers. So the other two reviewers would know who the third reviewer is, essentially. So that is an advantage because then if you're talking through your head, basically they can call your bluff and then they can also remember next time around, let's not get this guy involved in any kind of reviewing. Okay, but the reason for the anonymity also is sometimes if you are winding up, if your co-reviewer happens to be the guy with 10,000 citations and 1,800 papers, and they don't like the paper, and you are just a starting grad student or something, and first of all, I don't know why you're reviewing if you're a starting grad student, but so if you actually disagreed with their review, you may feel intimidated about defending your disagreement. So in that sense, they actually make it anonymous. So the idea is all three views are important, and the one level above, they will tend to know the names. So SPC would know who are the three reviewers, right, and they can take into account
So in this case, we know the names of all the reviewers, but when you are reviewing and there's a second reviewer, you are anonymous to each other. Okay. So anyway, the point is just you discuss about things, and if you can also defend your reviews to the other person. That's it. All right. So anyway, I'll send an email about this. If you have any other questions, you can ask me. All right.
Okay. So I have a sign-up sheet. I want to know who's actually showing up to the class. I know some names, but I'm trying to grade the papers, and they're never getting over. I mean, if the only people who are here are actually taking the exam, I should have been done grading. But apparently, a lot more people are taking the exam, maybe from Coursera or something. I don't know. So I just want to see. I want to see actually what's going on. For some reason, somewhere along the line, this became an half online class. I'm not sure. So I want to know who's actually showing up. Okay. So what I'm going to do today are two things. One is just a minor small thing, but it's important for us to understand. And then that is regarding the plate representations for graphical models. It's a useful thing to know because, in fact, you use plate representations when you go to LDA, for example. The second is, of course, we'll talk about Markov networks, which is a different representation for graphical models than Bayes networks, and we want to understand why they are connected. I mean, what the connections are. Okay. So the thing that I want you to understand with respect to Bayes network learning. So one of the interesting things that is happening in the Bayes network learning is if your network is not representing the hypothesis explicitly. Okay. Imagine the problem that you're trying to solve is the problem of basically coin toss, right? Coin toss. So if you have coin toss, what would be your network? You just have one variable, which is it heads? Okay, and then basically it's with some probability it will and then because so your Bayes network is this H. That's it. It's the full network. Okay, to specify this network, then you just need to provide the prior of H. So probability that H equal to true and probability that H equal to false. Right? This is a Boolean variable. So if heads is false, that means tails is true. Right? So this is the network. Now, the interesting question is, if you do have to, if you're taking the prior, if you're actually explicitly representing the hypothesis in the network, which is what Bayesian learning does, then so here is your, so let's say this is your first coin toss. You're about to toss the coin. and you're trying to figure out is it going to come heads or not. Now, that depends on theta. Theta itself is a variable now, right? And basically based on the theta's value, then the probability here would be so this is a Bayes network, and the probability h equal to true is equal to theta, right? Now notice now that the network now has both the domain variables and the hypothesis variables. You understand that? That's why Bayes learning it becomes just inference, because there is no hypothesis separate from the domain variables. Okay, now, and also notice that this is a discrete variable and this is a continuous variable, right? So this is a mixed continuous discrete Bayes network. Okay, now furthermore, since this, so now here I need to give probability h given theta. That's what you're supposed to give. pH given theta, it turns out to be equal to theta. Right? Okay. Now, that's not enough. I need to give theta value. I need to give a prior on the theta. Now, since theta is a real valued variable, okay, I'm sorry, it's a continuous variable. So I actually need to provide a continuous distribution, continuous prior distribution. That's what we said. So for this, the p theta is basically beta, alpha, beta, and the beta representation with alpha, beta parameters. That's what we were talking last time. Do you see what I'm saying? So we did this sort of without bringing back Bayes network into the front, but Bayes network was there. Okay, and then the prior for theta was this beta distribution, and then prior for h, of course, is in terms of theta. These are the domain variables. This is the hypothesis variable. So far, so good. Okay. Next question is, remember this random variable is what is the first toss going to be, heads or tails, right? If I am now going to have a second toss, that means I got more data. I tell you one more data point. How do I put this into this network? I need to consider one more. I need to consider so I'll call this H1, I call this H2. This is, under the hood, you may not have realized this, that when the extra data point came, the Bayes network expanded. You get the third data point, okay. Now the only interesting question is, of course, this network is much larger than this original just a red network. However, the thing that we have is independent and identically distributed. Okay, and so these heads are, one of the interesting things is, if I don't tell you the theta, is the second head toss dependent, your prediction on what the second point toss is going to do, is it or is it not dependent on what you have seen until now? What? It's not? It's not? Yes, prediction. The variables are dependent. The interesting point is, if you don't know for sure that I have a fair coin, then you are trying to figure out what the theta is based on what I am doing. And based on that, you are trying to, figure out the next coin toss. So the thing to understand is this network shows that very nicely and clearly. Okay, if I ask you in this network, is H2 independent of H1? No. Is H2 independent of H1 given theta? Yes. So there's some happiness in this, right? Because all this stuff about conditional independences that we built up is actually being used. Okay? Now the other interesting thing is that H2 is independent of H1, H3 is independent of H2, etc. Everything is independent of each other given the theta. If you don't give theta, they are all dependent on each other. Okay. Furthermore, as the network is increasing, you need to then provide additional information. Right? For example, for this guy, I need to provide the prior for H2. What's the prior of H2 given theta? Again, theta. You see what I'm saying? So in essence, what's happening is as the data is increasing, as you keep seeing more and more data points, the network keeps increasing in size. The network is increasing in size. Okay? In Bayesian learning, the Bayes network is increasing in size. Okay? Now, the interesting thing then is, how do I, so when I cannot just draw one single thing. I have to basically say, theta directly affects the ith point task. And it is true for I equal to 1, 2, 3, etc. all the way. Okay? So I want to basically say that a network which is structured that's kind of extending like this, I want to write it in some kind of shorthand form. That is the template, the plate representation. Okay? So the plate representation basically says that this network here is the same as this network. This is a shorthand notation. Okay? All I'm saying is theta essentially affects the point toss h, and you can put n here. That means there are n coin tosses. And as more and more coin tosses come, behind the back, basically this thing becomes a bit larger and larger and larger. So this is the extensional representation of this is this. When you see a network like this, think this in terms of first principles, in terms of inference, in terms of anything, you have to think this. But since writing this is pretty painful, you write this. Okay, so those of you who went ahead and started looking at LDA, I don't know whether you have done yet, you'd see a very nice compact representation with boxes inside boxes. So there is nesting of the structure. Okay, that's just so that you can feel that you have a nice compact representation. But as the points come, the network size just increases. So ultimately, you're talking about Bayes networks at the ground level like this. You just represent it this way. Okay. Now notice that not every Bayes network of this structure can be represented this way. If it was the case that theta has a different, for the first point task, it has a separate price. So if it's theta is the variable, for the first point task, the probability that will be heads given theta is, let's say, is theta. And for the second one is theta squared. The third one is theta cubed. The fourth one is theta power 5, whatever, let's say. That's what I wanted to say. Then I can't write it this way. Right? Because then each of the conditional probability distributions are different. This one is essentially saying these are identically distributed with respect to theta.
No, but with respect to deseparation rules, so given this network, Hn will always be independent of all the Hn minus 1 given theta.
That's true.
So how can we have a network like this and still say H1 the probability is theta and for H2 the probability is theta squared?
Why not? Independence has nothing to do with identicalness. So you kind of got, so here I just wrote this, okay, class, attribute A1, attribute A2, attribute A3. This is your naive Bayes classifier. Is there any reason to believe that probability of AI given class equal to Ci must be the same for all AIs? Not at all. But you still can say that given class A3 is independent of A2 and A1. Independence is different from the structure of the distribution. Independence is a higher order phenomenon. And that's the beauty of actually this whole entire graphical models. Graphical models don't care about the numbers of the probability distribution. They care about what independence assertions hold. Okay, that's a good question. I mean, if you're actually taking this seriously and if you don't have background in graphical models, these are the kind of questions you should ask yourself and answer it yourself, either yourself or put it up on the web or something. Okay, so that's called the plate representation. I wanted to bring this up to you. It makes two things. One, of course, is, this is sort of, you can think of this essentially as a quote unquote relational, a higher level, it's like higher level language for writing Bayes networks. Okay, but it will only work if in fact basically all of these guys have the exact same distribution. You could have essentially, given a network like this, you could have had different distributions at each node. But if you have the same distribution, then you can write this. Okay. Now, the plate representations can become actually quite interestingly, gaudy. Anyway, this is fine. Let's go. Where am I? Oh, there. Okay. So that place you only had one variable, h. Right? The domain variable was just one variable, h, which is it heads or not. But a normal domain, in a general problem, there can be many domain variables. Right? In fact, the domain variables themselves might correspond to a pretty complicated looking Bayes network. So when you see one data, you need the entire network. And if the next data point, you need the entire network reproduced. Do you understand what I'm saying? So put that in perspective. Remember, we can actually also have, here's a slightly more complex network. Flavor influences wrapper, right, in the candy example. Okay, now the interesting thing, of course, is if you're just doing non-Bayesian, but if you don't make the hypothesis part of the graph, then this is the network. If you make hypothesis part of the graph, then you need to ask yourself how many independent parameters are here, and for them you need priors, first of all. Okay, so just forget about these little things first. So I need a theta which basically is talking about what is the probability of flavor 1. Okay, I also need two, theta 1 and theta 2, which talk about wrapper 1 being red given flavor 1 being, let's say cherry, and wrapper 1 being blue given, wrapper 1 being red given flavor is cherry, and wrapper 1 being red given flavor is lime. Those two are independent properties. Right? So those are two numbers here, theta 1, theta 2, and theta. In the previous example, we only had one probability on which we needed to find a distribution. We found a beta distribution. Here you have three probabilities. Okay. The interesting thing is these, in putting it this way, I'm essentially, I took a bigger picture and cut them up, but here all I'm saying is my network looks like this. My first network, having seen just one data point, it looks like this. Flavor 1 causes wrapper 1. I shouldn't say that cause, but. And then theta is affecting the flavor 1's probability. And then theta 1 and theta 2 are affecting wrapper 1 probability. And the way it is happening is that here, probability flavor equal to red given theta is theta. Okay, and here probability that wrapper equal to red given flavor, what? Yeah, flavor equal to cherry is, I guess, theta 1, and probability that wrapper equal to, and then you actually have to write, because notice that for wrapper 1, how many parents are there? 3 parents. You should really be writing in terms of all the parents. Okay, but really the important thing is that wrapper 1 equal to red given flavor equal to cherry is theta 1, wrapper 1 equal to red given flavor equal to green, and the other one, lime, is theta 2. Those are the two probabilities that are being put. Okay, now these thetas essentially have to be, you need to put a prior on these thetas. In the way I wrote this, are these thetas, if I haven't seen any data, are the thetas dependent or independent? What? Independent. If I haven't seen any data, then they're basically independent. Okay, that means I'm assuming that the probability with which this is happening is independent of probability with this and probability of this. So then I can essentially put 3 different beta distributions as priors on each of these. Okay, so that is basically, that makes your life simple, because as great as Bayes learning looks in the beginning, these are all the extra disadvantages of Bayes learning, because now what used to be the background hypothesis variables comes and sits front and center as part of the network. And then you need to put priors on them. If in fact you want to say that theta and theta 1 and theta 2 are somehow connected, then you should have a network that shows that too. Suppose you think that theta somehow affects theta 1 also, then there should be a link from theta to theta 1, separate from that data points. You see what I'm saying? Okay. Now that is first point, that in this case, many times when there are multiple parameters, you assume parameter independence. You put prior on the parameters, but you assume each of them are independently distributed. They don't have to be identically distributed, but they're independently distributed. And since these are all binomial scenarios, we can assume all of these are beta distributions. Now what happens when I see the next flavor wrapper combination? When I see the next flavor wrapper combination, now that's my network. Next, that's my network. Okay, just as I said, as the data increases, the network is increasing in size. But the advantage is, it is indeed a pretty formidable looking network. It almost makes you think, I don't want any more data, because my network is increasing in size. Right? Okay. However, of course, if I were to put this in, a plate representation, right? Where is my plate representation? That's my plate representation. Right? Okay. Until now, you did not still see plates inside plates. We will get to see that when we get to LE. But it's the same idea. When there is a structure being repeated, you can essentially just shorten it, and that way you know what you need to specify this network. Clearly speaking, what you need to specify is the prior on this, a prior on this, a prior on this, a conditional on this, given thetas and the parent, and a conditional on this, given that. And then when it keeps increasing, you're copying the same CPTs and the same conditional distributions. Yes? What?
Given data, theta 1 and theta 2.
They will get it, yes.
Because we have a complete number of red that are there.
No, so you are saying that once you see the data, they become dependent. Yes.
I'm trying to explain how they are. As in, we'll have a fixed number of red copies with fixed number of green and red wrappers as well. So we'll get a number bound on them. That's how they get dependent. As in theta 1 plus theta 2.
But more importantly, just looking at the structure of this network. Okay, I can make them be dependent as I get data in. That's basically just the deseparation condition. It's the independence condition. Okay? Okay, so that is the point about this this idea that underneath the hood, the network is increasing in size. That's something that Bayes learning does. Okay, you don't have to do all of this when you don't think theta 1 and theta 1, theta 2 and theta are not random variables. If you don't think that they are random variables, you don't need to put them in the network. Which is why MLE learning, everybody loves it. It's so easy. But it has all sorts of problems because of all these regularization issues and so on. Okay, so doing the right thing is hard. That's what I want you to understand, that doing Bayesian learning is generally hard. In most cases, people still would prefer to do Bayesian learning, but they don't quite. Okay, by the way, since we are into Bayesian learning, I want to ask you the following question. In reinforcement learning, you had models. So in MDPs, you had a model. You're given a model and then you use it to do policy iteration, value iteration, etc. In reinforcement learning, you're learning the model and using it also to behave. Right? Okay, now what did you do at any particular point of time? If I asked you what is the model, you had to figure out the model from the traces, from what happened. How did you figure it out? So basically, you did this action 8 times, and 4 times it went into S1, 3 times it went into S2, 1 time it went into S3. So do you know the model? You knew the model. What did you say was the model?
When I take a particular action, this is the transition probability.
Yeah, so you found the transition probability, right? You said 3 by 8, 4 by 8, 1 by 8. Who does that? Who does that in all the learning algorithms we did just now? MLE. So without saying it to ourselves, we just did maximum likelihood estimate of the model. Do you understand what I'm saying? What if you actually have some idea about what actions do? You had a prior on the transition probabilities. Do you see what I'm saying? I mean, think about tossing the coin as an action in reinforcement learning. Okay, so I tossed the coin twice. It came heads twice. So you would say the model is that you'll always get heads. That's not true. And the only way you can say that's not true is if you were to allow for yourself to admit that you have a prior on the probabilities. Right? Now if you do that, then instead of having a single model at any given time, what will you have? You will have a posterior on the models. Up front there is models for the actions. The prior model, priors. So, if you have only one action, essentially, then there's a prior on what are the possible, probabilities you expect for this action to do, the transition probabilities. After seeing the data, you get a posterior probability on each of the action models. Okay? You see what I'm saying? So then, while doing learning, you essentially are going to be saying that based on my current exploration, this is the posterior distribution on the actions in this domain. And then I have to do prediction using all the models, just like you did it for the tossing coin. Now you can see how painful doing Bayesian things can be. Essentially, we are talking about having many different, basically infinitely many models of how this maze works. And with respect to each of those models, you are trying to find optimal policy. And then find the optimal expected policy with respect to the entire distribution. Is this hard to do? But of course it is hard to do. Is it the right thing to do? Actually, it is quite the right thing to do. MLE doesn't become right in reinforcement learning and become wrong for coins. The same arguments you gave against maximum likelihood estimation for coin toss holds there too. Okay, so there is an idea called Bayesian reinforcement learning. And if you hear that, you should shiver. computational cost involved in doing it. You see what I'm saying? This is the idea. I mean, I got into this by saying that doing the right thing can be quite hard, because Bayesian learning has many great properties, because you're never making an arbitrary jump to any specific model. But doing it can be computationally quite expensive. And this becomes very clear when what you are learning with the Bayesian learning is a posterior on the models of the MDP. And for each model, there is a different optimal policy. Now I'm asking you, what is your optimal policy? Then you need to consider expected value over the expectation of the different models, and then make the policy with respect to that. Okay? And there is an area with all of 8 or so people working on Bayesian reinforcement learning. And in fact, the textbook in the reinforcement learning chapter talks about Bayesian reinforcement learning. And if you go back to my reinforcement learning slides, there is one slide that I put in there which I just skipped over without talking about it, where I point out that how can you be sure, just based on the examples that you have seen till now, that the model for the action from S1 to S2 is 3 by 8. It's the same question. Just because you saw that the coin came up heads twice and tails once in 3 tosses, why do you expect that 2 by 3 is the probability of heads? Okay, normally you can say, well, I can weight large data scenario. I mean, have large data, then basically the priors don't matter. But that's exactly the wrong argument to make for reinforcement learning. Right? Basically, then you are saying, I'll just keep exploring for a while without at all exploiting my model. And after getting a huge amount of data, then I can do MLE on that. And the model I get that way would be fine. But the problem then is basically that you're exploring way too long. Okay? Okay. So you would like to, so there is this tension between trying to exploit what you learned, even though you only lived for a couple of epochs, versus waiting for a long time and then making up your mind as to how the world works. Okay, now we talked about the exploration-exploitation trade-off before, but this is different. This is another issue here where I'm basically saying that you don't actually know, just based on the couple of epochs that you have lived through, what the correct model is. And rather than wait for a long time, if you do Bayesian reinforcement learning, you can still do quite well with small data. Bayesian learning becomes very useful for small data. For the large data case, MLE is the same as Bayesian. Which also explains, for example, why you don't hear that much about Bayesian learning in Google sorts of scenarios, because they assume they have too much data. One of the things we'll find out is there is no such thing as too much data. It all depends on how many parameters you have to learn. Okay, this idea that we have too much data is a myth. Okay, so in fact, LDA does Bayesian learning, and it's basically language models. You think there's enough language to go around on the web, but it turns out there are also enough parameters to learn. Okay. Any questions? Okay, so this I am going to try and go as fast as I can. I don't quite know how. If not, we'll do a little more next week. But it's a useful thing to know, since I made so many references to Markov nets. And as far as I know, nobody teaches Markov nets around here. So I guess I should, because they're useful. Many of you, some of you may have heard of conditional random fields. Anybody? Okay. Conditional random fields are basically Markov networks used in discriminative fashion. Okay, and I've been making these side remarks on Markov networks before, so I thought at least a 1 class, 1.5 classes. I was hoping 1 class, but now we're already half class in. Anyway, okay. So what is a Markov network? Here, is a Markov network on 4 variables ABC. Okay, the structure of the network, but the important thing, I mean, in terms of just in representation, there are no directed edges. The more important thing is not how the structure looks, but what is the first question you ask if somebody gives you a graphical model? What's the first question you are supposed to ask based on all the stuff we did with the Bayes network? What's the first question you're supposed to ask? What are the conditional independence assertions that are built in? Right? So anybody can draw pictures, any pictures. The real question is, okay, what independence assertions does this structure show? So I can ask the following question: is B independent of D given nothing? That's one question. Second question: is B independent of D given C? The third question: is B independent of D given A and C? Those are 3 questions. You need to be able to answer all of them. Okay? How do you answer? And what is your intuition? I mean, if you have some intuition about this is basically these links, these edges must be talking about how they are influencing each other. Right? That part is same whether it is Bayes networks or Markov networks. Okay? The interesting question is, so do you think is B in this? If you think that A influences B and A influences D, and then C also B and C and B and C and D also influence each other, if you know that from this structure, you don't quite know how they influence. Okay? If I ask you, is B independent of D given nothing? What's your answer going to be? No. Right? Because A and C will be affecting both B and D. And so knowing something about B tells you something about A and C, which will tell you something about D. So they're not independent. Okay? Again, remember that the idea of independence, if you haven't spent enough time in probabilities and statistics, idea of extremely important idea. People think they understand it. You want to make sure you really understand. Independence only means that B will be correlated with D. That's all. It's not that I can directly predict D's values because I know B's value. Okay, so if you do the scatter plot, it won't be a nice rectangle, it would be something other than a nice rectangle. Okay, fine. So B is not going to be independent of D given nothing. Is B going to be independent of D given C? No, because A is still going to be playing havoc. Then the next thing is B independent of D given A and C? Yes. Okay, so essentially now if I do A and C, if I do A and C, what did I do? I essentially separated B from D by cutting AC off. This is a graph theoretic idea of, if I cut AC off the graph, is there a link from B to D? If not, then they are separated, they are independent. Right? I mean, again, think about the following thing. If you have 4 independent variables, A, B, C, D, what would the Markov network for those variables look like? What would the Bayes network for that network look like? No, so here is the question. So independent variables A, B, C, D, they're all independent of each other. So what's the Markov network look like? You said this, right? Yeah. I don't know, went off. Okay. So the Markov network would, where am I? Okay. I don't even know why it went off, but that's okay. So the Markov network would be A, B, C, D, 4 vertices. What would be the Bayes network look like? What? Same thing. Okay. So that guy passes. The rest of you don't pass this course because you have said this like without thinking by now. Okay. It's the same thing. So what does that tell us, by the way? What's the corollary of what you just said? An interesting corollary of what you just said. There are 2 representations, Markov networks, Bayes networks. and I had a particular real world scenario, A, B, C, and D are independent variables. I want to represent them, using these representations. You just said that they both can be represented either as a Markov network or as a Bayes network. This should start making you think, why am I coming up with a new representation if it represents, this example can represent either here or there. You have to keep that in mind. In general, you should not be happy unless I can somehow show you that there are certain things that cannot be represented in Bayes network and can be represented in Markov network, and vice versa. Otherwise, why do you need two guys? It's bad enough that already I gave you one example which can be represented in both cases. Okay? So the interesting part to know is that Markov and Bayes networks have a large overlap. That means given a specific probability distribution, sometimes it's possible to exactly represent it using a Markov network or a Bayes network. But there are always cases where it can only be represented as Markov network or it can only be represented as Bayes network, which is one reason why you need both representations. There are other reasons, but that's one reason. Okay, but the reason we were talking about this is that so if you go back to everything independent of each other scenario, right? Notice that I say A is independent of C because there is no link. A is independent of B because there is no link. So in this case, is A independent of C given nothing? Yes. In this case, is A independent of C given nothing? No, because B and D are falling on the path. So then if I remove B and D, then this graph would be just A separate and C separate, no links anymore. So then is A independent of C? Yes. Okay, so the thing to understand is in Markov networks, one beauty of Markov networks, which is pretty much the only beauty for them compared to Bayes networks, is unlike the D-separation condition, which is more complicated for Bayes networks. Okay, in Markov networks, this independence is directly connected to graph separability. Simple. And you all know graph separability, right? Given a graph, given a cut set, you remove the cut set at vertices, then you see if there is a link between the two variables that I'm trying to see whether they're independent or not. There's no more edges after I remove these middle guys. Then they're independent. Right? Okay? So that's basically the way you do the independence for Markov networks, the separability. Now that you figured that out, so every cut set turns out to be, if given, so if I ever ask you, is in some arbitrary Markov network, is a set of variables A independent of a set of variables B, given another set of variables C as evidence, then all I need to do is remove C, actually act as if I removed C from the network. Then see if there is any link left over between any pair of nodes from A to B. If there is, then they are dependent. If not, they aren't. Okay? This also explains why, for example, why is B independent of D given C? Well, let's see. I remove C. It's no longer there. However, there's still a link between B and D through a path. So B is not independent. Okay? So in that sense, Markov networks are very nice. The next question is, so once I figured out, that's the first question. The first question to ask about any graphical model is, what are the conditional independence assumptions? What's the next question to ask about any graphical model? What? Yeah, so what parameters are you going to put? What probabilities are you going to put? So the interesting thing is the moment I give you the topology of the network, you already can say that an infinite number of distributions in the world cannot be exactly, an infinite number of distributions on 4 variables in the world cannot be represented at all by this network. Do you see what I'm saying? Okay, because there may be, every independence assertion that this network says better hold in that distribution and vice versa. Only then can you represent it exactly. I can always come up with distributions on 4 variables which don't have this one-to-one correspondence between the independence assertions that hold in that distribution and the independence assertions that hold in this topology. So the moment I give the topology, I removed infinite number of distributions. So how many are left? Infinite number left still, right? So now I need to figure out, is a specific distribution I gave, is that captured by this guy? Right? To do that, I need to actually talk about something like in Bayes networks, you had something like CPTs, the prior. For each node, you provided some sort of a probability distribution given its parents. Okay, now we try to do that. Who is the parent for C? Right? So the thing to understand, actually this is something to understand, by the way, that there was this thick book. I wish I got the Bible on graphical models is Kohler and Friedman's book on graphical models. It's only 1,400 pages or so. Okay, so if you actually go into the details of the graphical models, you realize that in some sense, Markov network should be the ones that we should understand first. Then everything else looks like an extra, the kind of structure that Bayes network provides, which you got used to, such as for each network, just give its conditional given its parents. That doesn't make sense in Markov networks because there are no parents. What you really need for any graphical model is this idea of factorizations. This idea of factorizations. Okay, somehow I need to give, this basically, if these are, 4 Boolean variables, right? The joint distribution will contain 16 numbers, which add up to 1. Okay, I need to give you some number of small tables such that when I multiply them, I get this 16 number table. Was that true in Bayes networks? Was that true in Bayes networks? Who said no? Okay. So in Bayes networks, is it true that the full distribution was representable as the product of small distributions? It's not. It is. I mean, yeah, I don't know if you do not get that, really, you should ask for your tuition back and do some other course because you clearly didn't get anything out of this course, honestly. Okay, the whole point of Bayes networks was that it was completely factorizable. Okay, so here A caused B caused C, right? So there was a little table here which says A equal to true, this probability. And there's another table here which is probability B given A and probability B given not A. And then there's another table here, probability C given A, probability C given not A. That's the only tables. You multiply those tables, you got essentially 8 numbers. Of course, you could write this table as full table. So for example, you can write this as probability A equal to true is 0.7, probability A equal to false is 0.3. That's the table here. And then here, probability B given A is B given A is point, let's say 6, and probability not B given A is 0.4, of course, because it has to be one of them, and probability B given not A is 0.3, and probability not B given not A is 0.7. That's a table, right? So this is a 0.7, 0.3 table. It's a factor, and this is a 0.6, 0.4, 0.3, 0.7 table. That's a factor. And similarly, there is a factor like that. Say 2 by 2 factor here. Okay. So if I need to find out what's the probability of A, B, not C, I mean A, not B, and C. What did I do? I started with A, 0.7, not B given A is 0.4, 0.7 times 0.4, and not B, and then C given A is whatever that number. I multiply this number. Actually, this product, what I just did to this, so I took 0.7, 0.3, multiplied it by 0.6, 0.4, 0.3, 0.7, and multiplied it by, I'll make another numbers there, so 0.2, 0.8, 0.9, 0.1. Okay, it turns out that if I multiply this, I should get 8 numbers. How do I do it? You know, for example, if I need to get B, A, not B, and C, so I'm taking the A entry, I'm taking the entry here that corresponds to having A and not B. That's like a join operation from databases. So you join this table to this table using A as the natural join, as the shared variable. Now you will get, when you join that, you would then get PAB table. It's not probability, it turns out. It's just you get a table called factor AB table. The factor AB would correspond to essentially doing join over A between these two tables. And for each entry, you multiply the values corresponding to those two rows. You get a number. Then you then multiply this factor by this factor. Once again, the only join is A, because A is the only thing that's common. And that's how you get your 8 numbers. I sort of thought you got that, but no, that's basically the bedrock of factorization of probability tables. You see what I'm saying? That's ultimately what conditional independence assertion is speaking. They're essentially saying you don't have a prime number. It's made up of 8 factors. There's still infinite numbers which have 8 factors. But I can tell you a whole bunch of numbers that won't be having just 8 factors, for example. Okay, so now the only thing that's interesting in the probability, in the Bayes networks, is when I started, each of these tables had strict probabilistic interpretation. They're all conditional probabilities. They're all conditional probabilities. Okay? However, what you get in the middle looks like a factor, but it no longer has any probabilistic semantics. Do you understand what I'm saying? So here you wound up having factors which also, just as a bonus, became conditional probabilities. After that, in between, as you are computing the entire probability distribution by combining these factors, the intermediate factors don't have any probabilistic semantics. Again, at the end, you will get a probabilistic semantics for the factor. You see what I'm saying? Okay, so if you read something like a variable elimination algorithm, which essentially keeps track of these factors, Okay, and in between, during the intermediate stages, these factors have no probability semantics. By the end, they'll have probability semantics, probabilistic semantics. Okay, so if you got used to that, then my question is, so how am I going to parameterize this network? How am I going to parameterize this network? Okay, now all I would say is, instead of thinking that you gave here P, B given A, think of this as it was a factor over B and A. So here are the tables. This is a table, it's a factor over just A. Here is a table, it's a factor over A and B. Here is a table, it's a factor over A and C. And you needed a table which is a factor over ABC. To do that, you multiplied FA with FAB. In some sense, that multiplication is not a matrix multiplication, that is a join, really. Okay, if you multiply FA by FAB, you get F dash AB. Then you multiply F dash AB by FAC, you get F double dash ABC. That F double dash ABC is the factor you're looking for. This is what you did for Bayes networks. The beauty is, when you got the final factor, in the case of Bayes network, all those factors, all the entries added up to 1 exactly. Do you really care? You care that the numbers in the final factor all add up to 1? Suppose I tell you that here is the factor for ABC, 20, 35, 49. Can you make it into a distribution? Of course. 20 divided by 20 plus 35 plus 49. 35 divided by 20 plus 35 plus 49. 49 divided by 49 plus 20 plus 35. This whole thing I'm doing to get you to understand that the parameterization for the Bayes net for graphical models didn't really have to be probabilistic at all. It never really had to be probabilistic. It turns out that it could be probabilistic in the context of Bayes networks. It could be seen as conditional probability tables, and then it would work. But you could have done things without conditional probability semantics. Okay, and in which case, then what would have happened? In which case is that you would get a final distribution in an unnormalized fashion. You can normalize it, add up everything, and divide every entry by sum. You get normalized distribution, right? Okay. The reason I dragged you through this whole thing, rewriting the history of Bayes networks that you already thought you understood, is so that now, when I tell you that the way I'm going to factorize this is essentially provide what I call potentials. Now you might ask, what's potentials? Well, they're just potentials. You care what those numbers were, as long as you multiply them and you get some bunch of numbers, and then you can divide them all by the. So by the way, what is the minimum requirement for these numbers so that you can convert it into a probability distribution? Did you see that? As much independence I seem to have, as much freedom I seem to have, I still want these numbers to be positive. Because if I say 20 minus 20, 35 minus 44, I have no idea what to do with it. You see what I'm saying? Okay, so all I would then say is, really the thing that was needed for any graphical model is to provide factors. The factors should be positive numbers. And factors should be provided on subsets of variables in the network. Factors should be provided on subsets of variables in the network. And the typical idea is you will try to provide factors that sort of capture the interactions between particular subsets of variables. Okay? In general, if you ever find yourself providing, given a network like this, if you ever find yourself providing a factor on BC as input, you went wrong, right? Because B and C have nothing to do with each other. There is no connection between them directly. So there should never be any reason for you to provide a factor on BC. Instead, you should be providing connected things. Either you can provide FABC, which is fine with me, because B, C, A are connected. Or just provide FAB, FBC, and FA, for example. If you ever find yourself providing as input factors that are disconnected variables, then there's nothing, it's not that you're theoretically wrong, but the whole game, the exercise of this game is to provide an exponential number of probabilities with a much smaller number of independent parameters. Right? And so when you did this, you unnecessarily lost a chance to avoid overspecifying. Okay. Now, all this will tell you that all I needed is factors, and the factors should be connected sets of nodes. Do you have connected sets of nodes here? Yeah. Okay. So the way Markov networks are parameterized is basically you provide a potential on connected subsets of nodes. Without loss of generality, one can say that if you provide factors only on cliques, what's a clique? Yes, fully connected subgraph. Okay, if you provide factors only on cliques, that means subgraphs of this graph that are cliques, then you have not lost any generality. That means any probability distribution that has the independence assertions that this guy has can be represented by picking the right set of potentials. It's a pretty big theorem, but it turns out that's true. Okay, so basically here, now what are, so in this particular case, what did I give? I said all cliques, by the way. It doesn't have to be the maximal cliques necessarily. Okay, so in this case, I know actually the maximal cliques in this case are what? 2. Right? So I just gave you 4 potentials. So here's the question, just for sanity check. Could I also have given a potential on just D? Is D by itself a clique? Yes. So I could have given it on D too. Since my question is, do I really think, I mean, so keep that in mind. So it's not necessary that you only have to give potentials on the maximum. But if you just provide potentials on cliques, then you will be able to capture every distribution that has the the kind of independences that are in this network. Okay, so I provided for each configuration in that. So for the clique AB, I'm telling you if A is 0, B is 0, then I give a number 30. That's the potential. A is 0, B is 1, number 5, A1, B 0, number 1, etc. Okay, now the basic informal understanding is the bigger that number, the higher the affinity for that particular configuration to hold. Okay, if nobody else is saying anything about anything, okay, if BCD somehow disappeared at all, just left to themselves, are A and B going to be both, what is this table telling us? Are A and B likely to take different values or the same value? Same value. By the way, I call this, for reasons that I hope you will get, I call this the Mr. and Mrs. Smith, the movie example. You'll see why, hopefully. Okay, so think of A and B, for example, as Mr. and Mrs. Smith. So left to themselves, presumably, they will both take A equal to 0, B equal to 0. That's their affinity, presumably. Without giving away major suspense of that movie, it turns out that they first of all try to kill each other. Which is not exactly, sort of an indication of great love between them. Okay. So left to themselves, they would have been fine, but there are other variables at work. Again, without giving away a great amount of story, I guess presumably somebody tells this person, "I'll give you $10,000 to kill your wife," and tells the wife, "I'll give you another $10,000 to kill your husband." And I say, "Oh, the heck with it. I know that I like this guy, but $10,000 really is a useful bit of money." Okay. He's trying to say, okay. So this is A and B just by themselves. What is their affinity for their subconfigurations? Okay, and similarly, this is the affinity for B and C, C and D, D and A. Now, here is my interesting question. What about so B and C? So B and C will also take the same values just by themselves, right? And that's what these numbers are telling us. Okay, qualitatively, B and C would like to either both be 0 or both be 1. They want to go together. Similarly, however, C and D and A are the bad guys, right? C and D would rather be different than be same. And D and A would rather, again, D and A actually want to be the same. Actually, in this case, D and A would like to be either 0 or 1 together, but C and D would rather be different than be same. And the numbers there tell you how much of an affinity is there for those things. Okay, so now the interesting question is, so if I have this, then to get the full probability distribution, what do? I do the same thing that I did earlier. To get phi A, B, C, D, I multiply phi A, B by phi B, C. When I multiply phi A, B by phi B, C, think join over B. You get a join table. All of you, I hope, know joins. None of you know. People may not know databases, but they typically know. People may not know AI, but they typically know databases. You two excluded. Okay. But so you at least know join. And then for the join table, you know the numbers for each of them. Then you multiply that join table with CD. So you got AB times BC, you get ABC. ABC times CD, you get ABCD. ABCD times DA, you still get ABCD. But the numbers will be different. Right? You should do this. It's not very hard. It should not be hard at all. Okay, so PABCD, probability of ABCD is really given by probability, the multiplication of these. So if I say, what's the probability that A is to B is to C is to D is to? That would be given by the true entry from here times true entry from here times true entry from here times true entry from here. That would be the raw number. That much is easy. However, to make it the probability, I need to divide it by the normalization constant. The normalization constant is the sum of all the other probabilities, all the other ratios. You see what I'm saying? This is what I mentioned in passing several times, that this normalization constant for Bayes networks was what? You had this in Bayes networks too. Because I just told you that to get probability of A true, B false, C true, you just multiplied the tables and divided by a number. What did you divide it by? You divided it by 1. Because you know that they'll all sum up to 1. So you didn't have to think about, if you're always dividing by 1, then you don't need to think about the normalization constant. Here on the other hand, not more generally, you don't have that luxury. You need to think about the normalization constant. Fast forward to learning. At some point of time, okay, so what are the parameters in this network? Every number here, you could have put a different number there. If you're trying to learn this Markov network, given this particular example, and I keep giving you a whole bunch of this particular network configuration, I give you a whole bunch of examples. Okay, here is I just saw A true, B false, C true, D false. Now I just saw A true, B true, C true, B true, D true, and so on. I keep telling you how many examples I saw. Based on that, you are trying to compute these numbers. This is what you did for Bayes networks too, right? To do that, you did maximum likelihood and you did, your partial derivative. And the good thing was partial derivative got essentially unentangled. But that will never happen again because this guy Z will be there under every parameter. And every parameter is now dependent on every other parameter. Because the sum has to be the one that Z is. That's the entanglement that I was telling you. Even for complete data case, Markov networks, you actually need to do real gradient ascent. Okay, fine. So that's the way you compute these numbers. You should understand this. If you do this, this is the unnormalized distribution, and this is the normalized distribution. Okay? Now, my question is the following. So previously we said in Bayes networks, the factors had nice probabilistic semantics. Do these factors have probabilistic semantics? Of course they don't, because anybody can see that there are hundreds and 1500s, it's not probabilities. But suppose I actually somehow, put only numbers between 1 and 0. Then I would have made it look like they are probabilities. You wouldn't know any difference. Could they have probabilistic semantics is the question. Okay, now here's the idea. One idea is maybe this is the marginal of AB. So if I have a joint on ABCD, if I marginalize C and D from the distribution, then I get phi AB. You understand what I'm saying? So that I could say, well, I'm just giving the marginals. If I gave the marginals, that would basically tell me, taking all influences into account, whether Mr. and Mrs. Smith try to kill each other or try to get along with each other. Okay? So I do have the real distribution. Okay? I can compute the marginal over A and B. How do I do that? To get AB true, that means for the A0, B0 entry, I just take these 4, add up those numbers. For A1, I say A0, B1 entry, I take these 4 entries, add up, and so on. So I'll get 4 numbers. Right? Then I can compare that to phi AB. Okay? That's the marginal. And I'm not making this up. You pick up your calculators and add that up, and that will be the marginal. And that marginal came from the direct combination of the factors. According to this, what are we saying? We are saying that they're more likely to kill each other than to get along. They don't like to be in the same configuration. But according to this, they're actually likely to, they want to be in the same configuration. So, this is not the marginal. Okay. In particular, the last thing I want to show you today is basically this is a little example showing that it's actually not possible to give those little factors either marginal semantics or conditional semantics always. Sometimes they have to be marginal, sometimes they have to be conditional. And so you give up and just give them factors, which means I don't want to give any probabilistic semantics. Okay, so to do that, essentially, here is the situation. Think of this. This is a Markov network, XYZ. Okay, as I'm doing this, the next 2 minutes, think in the background about why wouldn't this argument hold for Bayes networks? Is this a Bayes network? It's not a Bayes network. There are no arrows. That should not take a lot of time to think. You need to put arrows. You can put arrows in any which way, and it turns out the argument I'm making here will not be applicable once you put arrows. Okay, so if you have XYZ, then this graph has the following independence assumption. X is independent of Z given Y. Nothing more. X is independent of Z given Y and nothing more. Okay, so if X is independent of z given by, then pxyz by chain rule can be written as py times px given y times pz given y. Right? That's by chain rule. So the question is, I want to write this in terms of potentials on pairs of nodes, let's say. So what do I need to do? I can, for example, combine this and this. It will become pxy. That would be sort of a marginal on xy. Okay? But then the other one would be z given by. That would be a conditional. Or vice versa. This would be conditional, that would be marginal. Okay? All this argument this is saying is, you can neither always go with marginals or always go with conditionals. In the case of Bayes networks, you could always go with conditionals. That's why you actually, so the second order point to understand is Bayes networks could have been specified without probabilistic semantics. The factors for Bayes networks can be specified without probabilistic semantics. But it was actually possible to specify them with probabilistic semantics. And that gives all sorts of advantages. You can ask, what's the probability you think that B will be true given A is true? And they'll give a number. That's a probability. And with that probabilistic semantics, you can define a consistent distribution. Come to Markov networks, that wasn't possible anymore. Because the more general case is the only normal factors, and in the case of normal factors, you get to write any numbers there. And these numbers just have to be positive. And the only thing you can say about this number is sort of an affinity between A and B to take that particular valuation if there is no other influence whatsoever, which is my Mr. example. Presumably, if nothing else, presumably you would like to say that they would like to take the same value. But then there are other things which are forcing them either apart or forcing them more together. And the only way you can figure that out is look at the full and marginalize. Okay? This is Markov networks. Okay, I'll spend part of next class going over the inference aspect and the learning aspect in Markov networks.